circuit. Here we have a MOSFET diagram. MOSFET usually look like this, and it has a gate, drain, and a source. MOSFET is basically metal oxide semiconductor field effect transistor. That's the long name of the MOSFET. And the MOSFET is used as an amplifier. MOSFET used as an amplifier. And for a MOSFET, the biasing is important. Biasing is helpful for us to set the Q point, and the Q point will decide how the MOSFET will work as an amplifier. So biasing is important, and this is to set the Q point. And then the Q point decide how MOSFET works as amplifier. As amplifier. Okay. There are several methods of biasing. I'm just gonna do the first method in this video. I will do the next methods in my upcoming videos. The first method is, what we do is we set the VGS to be fixed. VGS is nothing but the gate to source voltage. This is gate, this is source. In between that, there's a VGS voltage right here. Biasing by fixing VGS. Okay, for this type of biasing, what we do is we choose a circuit that has a voltage divider. Okay, so this is our MOSFET right here, and here we will have a resistor and the voltage divider resistor right here, and also here we have a resistor. This is the drain for the MOSFET, and whatever come from top is a VDD, and here this is the drain resistance RD, and this one is source resistance, this is RS, and then here we have the voltage divider resistance, that is R1 and R2, and in between the gate and the source there will be the VGS. This is minus. VGS, and this one connected to the ground. Okay, so the circuit is going to look like that, and this kind of circuit we use to biasing by fixing VGS. This is a simple approach to bias a MOSFET. Approach to bias a MOSFET. And here what will we do is we set the VGS to be fixed, and we will obtain the required amount of ID. That ID is the drain current. So what will we do is initially we increase the VGS until the required amount of ID is reached. Then once it's reached, we set that one to be constant. So it will get fixed after it reaches this required amount of ID. So VGS increased till the required amount of ID, that's the drain current, and once the sufficient ID is reached, we set the VGS to be constant. Okay, now if you look at the ID current equation, ID current is given by half times mu and COX W over L times VGS minus V threshold whole square, and here ID is the drain current, and COX is the oxide capacitance. VGS is the voltage between gate and the source. And the VT is the V threshold voltage. And W over L is the width over length ratio. Okay, and that's about ID current. And we can use the same method for two MOSFETs as well. We can use two MOSFET to do the same type of biasing, but it's not very common. But the thing is, when we do that, that's going to change the ID, because if you choose two MOSFET, the parameters are going to be different. In ID, this width to length ratio may differ, and that V threshold may differ, VGS may differ. So based on the current value is going to be different for two different MOSFETs. So let's see what happens if we use two different MOSFETs. Two MOSFETs. The V threshold and the W over L ratio, and also the oxide capacitance also will be different, and COX will be different. For two MOSFETs. So the graph is going to look like this. If you draw a graph in terms of ID and VGS, we may end up having a graph like this. One goes like this and the other one goes a little bit above, and if you pick a certain VGS value, this is VGS to VGS to ID, and if you select certain VGS, at that point the ID for the first one device, let's call this one device 1 and device 2. So for the first one it's going to be different, and at the same time for the second one it's going to be different. Second one meeting somewhere like this. So it's going to be different. So what we can say about it is two MOSFETs. We fix the VGS. Two different ID currents are obtained. two MOSFET will not have the same electrical parameters. Okay, and so from this one we can say the Q point is not stable for this one. Therefore this one is not commonly used. This method is not used. Okay, and that's it for this one. I'm going to go ahead and continue with the biasing in MOSFET amplifier circuit, the second part, in my next video. And that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.